Okay, let's start recalling tensor products, and I might well state the universal property for say non-commutative tensor products. Okay, and so this says something like that. Mm, let's call it okay. Let's have to start with the ring, I suppose. Let R be a unital ring, a ring with unity, but not necessarily commutative, okay? Which need not be commutative. And then we have a MR, a right R module, and NR, with the R on the left, a left R module. If R is commutative, left or right does not make any difference, but if it's non-commutative, there is a difference. And the reason is the order in which a product operates. Okay, right. Then, okay, let's define another thing. If P is an abelian group, so note that just an abelian group, not a module, a map, let's call it beta, from MR times and R, this is just the product, the Cartesian product, to P is called bilinear if it satisfies three conditions. The first thing, the first two conditions state that beta is a morphism of abelian groups on each component. Okay, so this means that beta, let's say A plus BC equal beta AC plus beta AC for all, okay, for A, B in M and C in N. Okay, so it's, which tells you if you fix the second component, then the resulting map from M to P is a morphism of groups, of abelian groups. Same thing in the second component. This time A is in M and B and C are in M. And and the third condition tells you that beta AR, well, no, let's use a different letter. MRN equals beta MRN for M, well, of course, little m M in N, and N in N, and R in R, okay? So there's nothing coming out of this, but you can, it's bilinear if you can shift from left to right, this thing here. And remember, it's vital here to have a right and the left module, as I explained last time. Then there exists an abelian group. This is important. This is different from the case of vector spaces because the tensor product which I'm going to introduce is just an abelian group. The abelian group. Okay, and the bilinear map, which are called iota, from the direct product, so the Cartesian product to this. Okay, with the property. Okay, now I need a little space. Let's clean this. With the property that that if beta from M to N P is bilinear, Okay, so P will be an abelian group, okay? And I have a bilinear map in this sense. Then there is a unique morphism of groups, abelian groups. We call the alpha, which makes such that the diagram commutes, which makes the diagram commute. The diagram which is coming presently. And the diagram is the usual thing. I may as well recycle this part. So this is iota, so they have more space. This is beta, okay? And this is alpha, okay? So in the non-commutative case, okay? So this need not be commutative. You take a right module, a left module, and you get an abelian group. This is just an abelian group. And from a bilinear map in this sense, you get a map which is linear mean, a morphism of abelian groups. So these two conditions are also stating that beta is a morphism of abelian groups on the first component and the second component. Okay, so that's a universal property. Good. I'm not going into the details, but you'll find the descriptions in several places. I'm not sure whether I have a good reference in the notes, but in case I'll add it. So what's the point now? So recall the point was the following. We start with G, a finite group, H, a subgroup of G, and W, a CH module. And whenever we want, we can translate this by saying that there is a representation raw, say, from H to GLW. Okay, it's remember that the two languages are absolutely interchangeable. Okay, so we want to obtain, in a certain universal way, a canonical way, a CG module associated to W. And then the heuristic argument is the following. Suppose that there is a CG module, so if you want a representation, V, okay, such that W is a subspace, mean just a vector subspace of V, okay? And then what we can do, of course, W is a module for CH, for the group algebra for the group H, but it need not be a module for CG. And we know that say the product WCG, okay, is then a right, all these modules are right modules, is then a CG module. But rather trivially so, because it's the CG module generated by W. And it's generated in the same way of vector spaces when you have a subset and then you take all linear combinations. So this consists of all linear combinations, say sum from I1 to N, Wi sigma I, where N is in N and Wi are in W and the sigma I are in CG, okay? It's rather easy to see that that any CG submodule of V, say submodule of V, this I have just added, okay? Martin read the terms that I've just added. It's just it's easy to see that that if W is contained in a CG submodule of V, then it contains this, and this is quite clearly. I mean, it's not difficult to see that it is a submodule, a CG submodule, because I mean, if you take the sum of these two things, they are already of this form, and if you multiply by an element of CG, of course, is again an element here, okay? So this WCG, the set of all these sums where n is allowed to be any natural number, and you take the Wi in W and the sigma in CG, is a CG module. And you can describe it in the following way. Okay, so this is a finite group. So everything is finite here. In particular, the number of cosets of H in G is finite. Okay, so let's take the index of H in G to be n. No, well, okay, okay. Let's call it K. Okay, just not to clash with this, and let HT1, HT2, HTN be the right cosets of H in G, okay? Where I take T1 to be 1, okay? Because one of these cosets will be H. So let's assume it is represented by 1, okay? I could take any element of H to represent the coset H, but this is simpler. The set T1, T2, Tn, I don't remember whether I have already used this term, is called a transversal of H in G. The reason why it is called a transversal is because you have G, and then you have the cosets, okay? These are the cosets of H, right cosets. And a transversal is something that picks one element for each coset. So it's something transversal to the coset, which you suppose move. So the cosets move up and down, and this moves left to right, something like that, okay? And of course, it's not unique, because you could replace T2, for instance, with any element from HT2 and still get the same coset, okay? So we have this. And so when we take a look at such an element of WCG, so let us take an element of WCG. So this is something of the form sum for some n, so for some n, etc. This Wi sigma I. But the sigma I, okay, now I'm going to have, okay, I hope I don't complicate the notation too much. So the Wi are in W, and the sigma I are in the group algebra. So the elements of the group algebra, you can simply write as, okay, I have to have several indices, AIG, say, okay, G, okay, so the sum over G, but, okay, let's fix the notation on the previous slide. This we call T, script T. Okay, this is a transversal. Okay, is this set, and you can rewrite this with for H in H and C T in the transversal. So I don't name T1, T2 the objects. But, well, no, let's do it like this. Well, okay, so H in H and one and I from 1 to J from 1 to N. Okay, so I have AIG, and I write an element of G as an element in H and an element in TJ. Okay, there's this can be done in a unique way. Okay, because the H, T, Tj are all the cosets, and then every element is in a single coset, and then can be represented uniquely as an element of H times an element of Tj. Okay, so if we copy this here, well, I should move this, but I'm not sure I can do it properly, so I'll leave here. So we find ourselves with this. So H in H and J from 1 to N. Okay, and we are working here inside remember, this is a subset of V. So these are, we can move these elements inside. And so we get something like this. Okay, so, sorry, this is a, let me correct a misprint. I have changed the number. So K is the number of you see here, K is the number of cosets. There are two indices n, okay. So we can rearrange here the sum, and so we can have the sum from J1 to K, okay? This is Tj, and then here inside you will have the sum. Okay, this G is HTJ, but I'll leave it like this. And where, okay, WIH, where A ranges in H and 1 goes from 1 to N. Okay? And note that these elements are in W, because W, remember, W is a CH submodule. So if you take an element of W multiplied by an element of H, and then these are complex numbers, okay, of course these are complex numbers, and then you're still in H, okay? So this element is in the following object, W times T1, which is 1, but doesn't matter, plus W times T2, and so on. No, not to call tensor product, simply product. Sorry, tensor product will come later. Okay, this is W, which is WT1, and then, okay, because it's a sum of elements inside here. Perhaps there's something to be noted here. So this, by assumption, is a CH module. Okay, the others are not CH module, but we'll see that this plays a role later. Note that WT for T in this the transversal T1 TK is an HT CHT submodule where HT is the usual conjugate. And the reason is that if you take, if little w is in big W and you multiply by an element of this, okay, these two simplify, so you get, and this is in H because, sorry, not in H, this is in W, because W is a CH module, so this is in WT, okay? So these are not CH modules, but they are modules for the conjugates. This will play a role as we get along, okay? So what we have found that if we start with, if we have a CG module V, such that W SCH module is a subspace of V, then inside V, we have this CG module, okay? Let's rewrite this here. So inside the CG module V. There is a CG submodule, WCG. Remember where W is a CH module, which is W plus, this is just a sum, not nothing more. Where I remember this is the set of a transversal, okay? This, which is the sum, T1 is one here, of this module for this group algebras. Now the point is that, okay, we are talking modules, okay? And we are, so for a while I will be speaking of a induced module, but then we'll switch to representations. And the idea is that definition, WCG is the module induced by W. Okay, sorry, let me rewrite it correctly. Is the CG module induced by the CH module W if the sum here is direct, which, recall, means that is for each j, we have that WTJ intersect with, okay, let's write T1. T1 is 1, okay, but I'll write it for simplicity. And I'll use the annotation that you should be used to. I write what is called here, well, whatever, a cap here to mean that this is not here, okay? This is 0. So a direct, I mean, when there are just two components in a direct sum, you simply say that the intersection of one with the other is 0. It's trivial. When there are more, you have to claim that for each j, each component intersects the sum of the others trivially. So this means omitted. Okay. This is a hat, okay? I mean, the word was not coming to my mind, but this is a hat. A hat means that this component, this is not here, okay? So the sum, when the sum is direct, we say that CG is the CG module induced by the CH module W, okay? It's, I mean, given a CH module W, there are many ways in which the W could be a submodule of a CG module, and this is a particular case, this induced business, but it's very important. It's very useful in practice, so the definition will justify itself. Now, my claim is the following claim. Oh, in the following, I'm taking a line of thought which is not written in the notes yet, which is a cross between the approach with tensor products and the approach, another approach that I wrote down a few days ago, which is due to Jean-Pierre Serre, I think it was Belgian mathematician, yes, a Fields medalist, so the equivalent of a Nobel Prize winner. And it's a very nice approach, but I think a mixture is probably best suited here. So my claim is, if W is a CH module, and we have the notation GH and so on is constant in the last few slides, then, okay, then I will write down, okay, is the, up to isomorphy, induced I left a space here to write what this object is the induced CG module. And what's this? Well, you take W, which is the left CH module, okay? You take the tensor product over CH. Remember, this means that you can take an element of CH, which is on the right here, to the left here. And here what we take? We take CG, which is, remember, this is something I mentioned at the end of the previous lecture, which is a bimodule. So it's a left CH module and the right CG module. This is not really as complicated as I'm trying to make it appear. It's simply that you have this group algebra, and you can multiply on the right by the element of the group algebra, and you can multiply on the left by the element of CH, which is a subalgebra of this, simply linear combination of elements over H. So this means simply multiply on the right by element of the same group algebra, multiply on the left by elements of the group algebra of H. Okay? So let's see why this is the case. Because you see, let's take a look at an element here. Okay? I'm not going into all details, but you'll see how it works in some detail. All right, so an element of this tensor product will be a linear combination of elements of the form well, you are used to the fact that in a tensor product, for instance, of vector spaces, not all elements are simple tensors. There is, it is not true that even if you just take vector spaces, an element of the tensor product is the tensor product of one element here and one element here. But you have to take linear combinations. So it's not surprising that the same holds here, and of the form W times sigma, okay? For W in W and sigma in CG. That's how we describe things earlier, okay? And what's this simple tensor is the iota of W sigma, okay? Remember the universal property on the first slide on the first board today. This is just the image of this pair, okay? But we'll get back to that later. Okay, of this form, so sigma in CG, and as before, we write sigma as, let's do it directly, as G, this time is easier, H Tj, okay? So, so sigma is an element of the group algebra, so it's a linear combination with coefficients, with complex coefficients of the elements of G, but you can split an element of G as an element of H times an element of the transversal. There is this means that this element of G is in the coset H Tj, okay? So when you look at this element, you can do exactly what we were doing a moment ago inside the this CG module V. Okay, this is, well, this is also over vector spaces, so this element can go outside or whatever they please, but since it's a tensor product over CH, which means an element of H that we find on the left here can go to the right here. So this means that this element H is going to go to the left, okay? And you'll find yourself with something like this. Okay, it's in red, but why not? And let's see. No, let's, I do it in black and I'll do it correctly. So this is the sum over, let's see. Okay, H in H, J from 1 to K, W, well, let's write the complex number on the left. So I've taken everything on the left, okay? Because this means that elements of H and element of the complex number can go to the left, and this is what I've done. And note that this lies where? Lies in this object W times T1, okay? Because it's a linear combination. I mean, it's a linear combination of elements which are in W times T1, okay, plus W times T2, plus and so on, W times Tk, okay? It's more or less what we were doing before in the CG module V, but this time we are doing it inside this tensor product. Claim this sum is direct. And so this means that this is the induced CG module, because let's get back. The point is, we say that this module is induced if the sum is direct, okay? And I claim that this sum is direct. So we have found a way of representing a place where this induced represented CG module exist. I'll do the proof in the particular case. For the particular case, when W is an irreducible CH module. Because it's simpler, but it would be not too difficult to extend this. Why I'm taking this? Because then, remember that CH had this property that it contains a copy of every reducible module. We spoke mostly in terms of representations. CH is a direct sum representation of irreducible representations where all the irreducible representations appear, okay? So W will be, or is, a CH sum module of CH, okay? Now, okay, so remember, we want to prove that this is direct. But we first work inside CG. We're going to use the universal property. Okay, I'll explain when it comes to that. Now consider an element of CG. Okay, consider an element of CG. And as before, this is of this form. And so we can write it as in this form. Okay, so and note that this is lies where? Lies in the sum from J to K, AG H, yes, will sum, okay, just a second. Okay, so note, this is in containing what? This containing, you see, this is an element of CH, okay? So it's containing CH T1 plus CH Tk, okay? But the point is, every element of sigma can be written in a unique way like this, and a unique way like this, Okay, so since the writing of an element sigma in this form are unique, and this goes back to the fact that every element of G can be written uniquely as an element of H times a transversal. The reason being that an element of G lies in a single, remember, right cosets are a partition, okay? Well, let's write it here. Right cosets are a partition. So if G in G is in the coset HTJ, then it can be written uniquely. As G equal HTJ with H in H, okay? So there is a unique coset in which G lies because cosets are a partition, and then of course there is a unique H, which is just G times the inverse of Tj, okay, in H. So since the writing in this form is unique, this means that this is a direct sum. Okay, because another way of saying that a sum of vector space in this case is direct is to say that the expression of an element as a sum of elements in each component is unique. Okay, another way of saying that is direct. Okay, uniqueness. Same thing as saying direct sum. Uniqueness is another way of formulating this condition here. Okay. If you look at the proofs, these conditions tells you that an element of this sum can be written uniquely in the form in this form. Okay, so it's the same thing formulated in a different way. Okay, good. So this is direct sum, but since W is a CH modulo of CH, so let's say next. So this is a direct sum. Which means that the elements here can be written uniquely in this form. And also, WT1 direct sum, WTK is a direct sum. As W is a submodule of CH. I mean, it's clear. You take a submodule of this and a subspace of this. I mean, you can write the elements uniquely here. If you take these elements, of course, uniqueness is inherited by the previous situation. Great. But now, consider now, so we have this tensor product here. I write it in this form for simplicity, but that would be a few things to be added. And now you know that the map beta, okay, which goes to WCG, which is exactly this. This is bilinear. Or which maps? This is the map that takes, I'll take just an element, a particular element. I just take a linear combination, which sends this to this is bilinear, okay? This is quite obvious because, I mean, it's multiplication. This is simply multiplication in the group algebra. And then, of course, it's bilinear because the two linearity conditions are simply the distributive properties, and then the fact that you can move an element from right to left is because you have an element inside here, okay? So it's the associativity, okay? So this is bilinear. No, well, okay, sorry. Back, there's a mistake here. Let me rewrite this. I was too quick. So you take the direct product of this, okay? So you take an element here, and this is bilinear, okay? Sorry, I was too quick. So, I have just rewritten this part. The tensor product will come in a second. I was skipping a step. So you take the direct product, simply the Cartesian product of this, and if you send this to their product, then this is bilinear in the sense that I defined earlier. But if you have a bilinear map here, then this means that there is a homomorphism of abelian groups by the universal property of tensor products. There is a morphism. Let's call it for the moment of groups, abelian groups, which makes the diagram commute from W tensor CG to this, okay? Which does exactly the same what I was saying. I mean, if you take a decomposable tensor, which is the image of this under the map Iota, it simply sends it to the product, okay? And my claim is that, so remember that this object, we saw it's the direct sum of, no, sorry, it's a sum. Okay. My claim is that this map is injective, okay? And so it will turn out that this is also a direct sum. Or let me think for a second. Okay, yes, because you see, okay, claim this alpha, this is alpha, okay, in the notation of the universal property. Claim alpha is injective, and thus this is a direct sum. Okay. And why is alpha injective? So this is an exercise on the universal properties of tensor products. Sorry, I'll need a couple of minutes more, because if you take an element here, where the Wj are here, and you apply alpha to this, you obtain some Wj Tj, okay? And if this is 0, okay, since this is a morphism, it's enough to check the kernel, because I mean, what this does, it takes an element W tensor sigma to W times sigma. So if you have an element here, it will be taken by alpha. Each element tensor will be taken into the product. But remember, this is a direct sum, okay? This is in the direct sum that we saw, T1, the direct sum in, so if this is 0, this is a direct sum in CG. And if this is direct sum, it means that that if this linear combination is 0, then each component is 0. And for this to be 0, you need the Wij to be 0. So Wj equals 0 for all j. And so this means that this element is 0. And since this is injective, it's I'll skip the details, but the end result is since alpha is injective. Okay, it's what I had written here, no need to repeat it here. But it's not difficult to see that since alpha is injective because of this simple argument, then this is also a direct sum. So this means this is the induced representation. But remember, this is just the tensor product. So let me finish by saying it will be much more concrete tomorrow. So the tensor product of W with CG, which to be absolutely precise is this object here. And I have to add something about this. It will be the induced representation, and we'll see tomorrow that this implies that that there is a simple formula for the character of these representations in terms of the character of the representation of W. So this has been a bit dense, but tomorrow we'll relax a bit, working with characters, and it will be much more manageable. Okay, that's all for today. Thanks.